1, quiet on the set. Physics, take 2, quiet on the set.
No, not ballooning, ballooning. Brooke, you're... All right, so what we are going to look at now is we're going to try to make a connection between Coulomb's law, which is what you learned in the lab, and the fields that we've been talking about, and see if we can make some connections between what's happening there. All right, so we did learn about Coulomb's law right here, KQ1, Q2 over R squared. Let's consider two charges. Okay, so let's take one charge that, let's just say that it's 2 microcoulombs, and let's take a second charge, and let's say that it's -5 microcoulombs, and that the distance between them is about 2 centimeters. All right, so we can go through this. We can work through this using Coulomb's law. We can put it into Fe, so the force, the electric force, it's Fe because it's an electric force, is equal to K, which is given to you. This will always be given to you. It's a constant, 9.0 times 10 to the 9th, times Q1, and Q1 is one of those charges, so 2 microcoulombs, so 2 times 10 to the -6, times Q2, and Q2 is the second charge, which would be -5 microcoulombs, so times 10 to the -6, and then we're going to divide it by the R squared, the distance between them, all right? And so the distance between them is 2 centimeters, so that's 0.02 squared, just like that. And then we're going to go ahead and punch that into our calculator here, all right? And I got -225. All right, -225. Now it is a force because I put this in coulombs, that in meters, and this in the SI units. Then my units should be newtons here. All right, now you'll notice that the answer came up as negative. What that means is what we already knew. A positive and a negative attract. And so when you see a negative in front of your force from Coulomb's law, it just means that the two objects are attracted, that they're going to be drawn towards each other. You actually could just do positive numbers everywhere, and then in the end, you could say, oh, if it's attracted, then I just need to say it's attracted. And if it's repulsed, then I just say it's repulsed. So it's up to you. Really, all you need to do is recognize, that negative is the attraction of two objects. Now, that's Coulomb's law. That's the force. But where does fields come into this? Well, we can do a similar thing. Remember we did for gravitational fields. We said, well, I can have the gravitational force, but I want to know what the influence of this object is without a second object there. So what we can do is we can say, well, let's just take out that second object. If I want to know what the field is like, or the field strength for this electrical charge, the 2 microcoulomb charge, it just means that I want to take this one out. Okay, so I'm going to take out this guy right here. And that would give me the strength of the field at this position of 2 centimeters. Of course, I could find the strength of the field anywhere, at 1 centimeter, at a meter away. I could find the strength of the field anywhere. The key is that we're taking that force and we're dividing per unit charge. We're dividing by the Q2. So very similar to your gravitational field, we're going to create an equation for electrical field, and that's usually shown by a capital E. The electrical field is KQ over R squared. And notice that Q here, right? Q here is the charge that's creating the field. Okay? The other charge isn't important. This just gives you the strength of the field. And just like what we saw in when we drew those images of the fields, right? We notice that as we get closer, R will get smaller, and as the bottom of your fraction gets smaller, it should make your total field bigger here. And so the field will be stronger the closer you are to that initial charge. Okay? Remember, please, that R is always the distance from the center of one to the point that we're looking at, or the center of the other object, just like it was when we were looking at gravitational fields. All right? So the connection I want you to make is that this is very, very similar to the gravitational fields, that we can demonstrate it in the same way that we're talking about an electrical force, which is KQ1, Q2 over R squared, which we showed in the lab. We can get the field by dividing by that extra charge there, and we can calculate the strength of the electrical field. All right? And so that's what you're going to practice in tonight's homework is, or I guess it could be classwork. You're going to be practicing calculating the field strength and recognizing that closer to the object, your field is stronger, and the further away you are, the weaker your field will be. All right? And I think that's about it for this video. Why don't you go ahead and move on to your next step.